Today we're going to continue with section 9.1 and polar coordinates some more. And we're going to start looking at how we can convert between polar and rectangular coordinates. We're going to look at how one point can be named in one system versus the other. We think of these systems as being placed on top of each other. And we talked on the first day about how we put the pole at the origin of the rectangular system and the polar axis is on the positive x-axis. So we think of them kind of sitting on top of each other. So here we want to convert from polar to rectangular. So when you're given polar, you're given r and theta. Theta tells you the angle from the polar axis to the terminal side, and r is the radius, is the distance along that terminal side. So this point is found by rotating theta and then going out r. If I want to change that to a rectangular system, I can think about how the rectangular system by thinking about this right triangle. In the rectangular system, you start at the origin, you go across x and up y. If we look at this right triangle, the legs are x and y, the hypotenuse is r, and this angle is theta. This should look similar to some of the things that we did in chapter 6 with unit circle trig. So here, I want to find a way to write the name of this coordinate in x and y coordinates. So I want to know what this x length is. I know r and theta, and I want to find x. X is the side adjacent to theta in this right triangle, and r is the hypotenuse. So the cosine of theta is equal to adjacent over hypotenuse, x over r. And if I took that equation and multiplied both sides by r, I would get that the x coordinate is r times cosine of theta. And then I would want to find the y coordinate. The y coordinate can be found with this length over here, which is opposite of theta. So sine of theta equals opposite over hypotenuse equals y over r. And again, if I multiply the r to the other side, I get an equation that says the y coordinate is equal to r sine theta. So these two equations can be used to find the x and y coordinates. And they will automatically give you the correct signs because, for example, if a point is over here in second quadrant, cosine is always negative in second quadrant, so the x coordinate will be negative. Sine is always positive in second quadrant, so the y coordinate will be positive. To do these problems, you also can use the 30, 60, 90, and 45, 45, 90 ratios. So we're going to kind of look at two different methods for doing them, and then you can do them whichever way you are more comfortable with. In a 45, 45, 90 triangle, I'm going to kind of go back to a geometry approach. In a 45, 45, 90 triangle, the legs are both equal to each other. We'll call them both x. And if the legs are both x, the hypotenuse is the leg times the square root of 2. So the legs are x, the hypotenuse is x times square root of 2. In a 30, 60, 90 triangle, 30 is the smaller angle, the shorter leg is opposite the 30. 60 is the larger angle, that's the shorter leg times square root of 3 gives you the longer leg, and then the hypotenuse is twice the shorter leg. So I'm going to do the next couple problems using both methods, and then it's up to you which way you decide to do them. If you're really good with your unit circle and know your values off the top of your head, it might be better to use these equations. Some people like it really visual and use the triangles. So here I want to take the point 6 pi over 6 and convert it from polar to rectangular coordinates. So if I'm going to use the equations say that the x coordinate is r cosine theta, and the y coordinate is r sine theta. So I plug into those two equations, and now I need to know the sine and cosine of pi over 6. Pi over 6 is 30 degrees, first quadrant, makes a 30-degree angle with the x-axis. So when we did unit circle trig, this is 1/2 and square root of 3 over 2, the hypotenuse of 1. I can use that reference triangle to substitute for these values. And again, if you know these values, this is a real quick way to do the problem. So here I have 6 times the cosine of pi over 6. Adjacent over hypotenuse is square root of 3 over 2. Here I have 6 times the sine of pi over 6. 1/2 over 1 is 1/2. And then I'm just going to multiply my x coordinate. 6 over 2 is 3, square root of 3. My y coordinate, 6 times 1/2 is 3. So this point is 3 root 3, comma 3. That's one way to do the problem. The other way to do the problem is to graph the point 6 pi over 6. So 6 pi over 6 is a point that on the pi over 6 angle that is 6 away from the pole. So I'm going to label this length, the radius, 6. The angle in here is pi over 6, or 30 degrees. I'm going to drop a perpendicular to the x-axis, and this is a 30, 60, 90 triangle where I know the hypotenuse. And again, if I know the hypotenuse is twice the shorter leg, and then shorter leg times square root of 3 gives me the longer leg. So I take the hypotenuse of 6, divide it by 2, and then take that shorter leg and multiply by square root of 3. I just need to be careful with this that I keep track of the signs. I'm in first quadrant, so everything's positive. It's not an issue. Now, if I look at this picture, my x coordinate is this horizontal length, and my y coordinate is the vertical one. And I get the same answer either way. So either method works well. Over here, I have the point -4, negative pi over 4. If I plug into the equations, x equals r cosine theta, and y equals r sine theta. I have to find the sine and cosine of negative pi over 4, which is down in fourth quadrant at a 45-degree angle. So again, if we make the hypotenuse 1, these legs are root 2 over 2 and root 2 over 2. I'm going to plug in here, and I have to be careful if I'm going down, make sure I make that side negative. So x equals -4 cosine is adjacent over hypotenuse, root 2 over 2. Y equals -4 times sine of negative pi over 4, which is opposite over hypotenuse, negative root 2 over 2. When I multiply this, the 4 and the 2 cancel out, and I get negative. Here I get negative 2 root 2. Over here, negative times negative gives me positive 2 root 2, and that's the name of that point. Now, if I wanted to do this using the geometry method, I have the point -4, negative pi over 4. I'm going to draw that point first. So in my polar axes here, negative pi over 4 is down in fourth quadrant, but with a radius of -4, I'm actually going to come up 4 in the other direction. So this point is up here in second quadrant, 4 away from the pole. I draw in the legs, this right triangle, and because this is a pi over 4, this is a 45, 45, 90 right triangle. In a 45, 45, 90, the legs are both x, and the hypotenuse is x times the square root of 2. So if the hypotenuse is 4, I want to divide by square root of 2 to get the leg. Take 4, divide it by square root of 2, rationalize, and simplify the 4 over 2, and you get 2 root 2. So in this triangle, the legs are both 2 times the square root of 2. Then I look at the picture and I see I'm going to the left, so this side must be negative. I'm going up, so that leg is positive. So my answer is the x coordinate is -2 root 2, and the y coordinate is positive 2 root 2. And again, we get the same answer either way we do it. One advantage of doing this kind of in this geometric method is that you get the picture of where the point is. One more example, 790 degrees, and these angles might be given in radians, they might be given in degrees. When it's one of these quadrantal angles, a multiple of 90, a multiple of pi over 2 radians, the best thing to do is just draw the picture. I have Let's make that line vertical. I have a 90-degree angle for theta, that's here, and I'm going out 7. So my point is 7 in this direction. It's up here where this length is 7. I don't need to use the formulas to find the x and y coordinates of that point. It's a point on the positive y-axis, so its x-coordinate is 0. It's going up 7, so its y-coordinate is 7. There's really no work involved in finding that point in rectangular form. We're going to start going from rectangular to polar today and then do more of that tomorrow. So here we're just going to look at the quadrantal angles. And what I want to do, these are points where I'm giving you the x and y coordinates. This point has a positive a value and then a y coordinate of 0. Here, when I'm on the positive y-axis, the x is 0 and the y is a positive number. Here I have x is a negative number and y is 0, and down here x is 0 and y is a negative number. If I want to name these in polar form, I need r and theta. And when we do these problems, I'm going to have you write your angles or write your coordinates so that the r is always greater than 0 and the angle is between 0 and 2 pi. We're going to go always in the positive first rotation. If you check answers in the book, some of them may have negative angles, but we're going to look at this rotation. So here I want to name this point. How far is it from the pole? That's the r value. Well, its x-coordinate is a. That is the distance from the origin. So that r value is also a. Then I want to name this angle that goes through that point. If I'm going between 0 and 2 pi and theta is greater than or equal to 0, that angle is 0. It's 0 radians, it's 0 degrees, either way. In this point on the positive y-axis, my angle goes this way. So this is either pi over 2 radians or 90 degrees. And how far away from the pole is the point? Whatever the value of a is. So this point is either a pi over 2 if I'm answering in radians, or a 90 degrees if I'm answering in degrees. Here, I'm going to rotate around to this terminal side to get to this point. So that's pi radians or 180 degrees. And the distance from the origin out to negative a 0, the distance is the absolute value of negative a, which is a. So this is a pi, or in degrees, it's a 180 degrees. And then the last example, if I go down to the negative y-axis, that rotation is 3 pi over 2, or 270 degrees. And again, the distance from the origin to 0, negative a is the absolute value of negative a, which is a. So my r is a, and my angle is 3 pi over 2, if I'm in radians, or my angle is 270 degrees. Just quick example, what does this look like when there's numbers? The point negative 6, 0. I go out negative 6. Here's negative 6, 0. And I want to change this to polar coordinates. So for polar coordinates, I need the radius and the theta. What's the radius? It's this length, 6. What's the angle? The rotation to get to the negative x-axis is pi. And I'm done. 0, 5. It's up here, 5 away from the origin. What's the radius? The distance from the pole is the distance from the origin, 5. What's the angle? Since I'm on the positive y-axis, that's 90 degrees or pi over 2 radians. So for today, you're going to do a delta math assignment, and the only ones that you're converting to polar coordinates today are the ones that are on the axes. We'll talk about the ones that are not on the axes tomorrow.